So good afternoon, everyone. My name is Sara, and I will be your host for today. I would like to thank you for taking part in MDPI's water webinar entitled Climate Change and Water Resources, Evidence, Impacts, Adaptation, which is based on 3 special issues. If you're interested in contributing to this topic, all the information is available on the webinar's webpage. The webinar will be chaired by Professor Dr. Athanasios Loukas, and the speakers for today will be Professor Dr. Demetris Koutsoyiannis, Professor Dr. Garrote, and Professor Dr. Antonio Cancelliere. We will have time for questions from the audience, moderated by today's chair. So if you have any questions for our speaker, please post them in the Q&A box at the bottom of the screen. And please remember to mention the name of the person to whom you're addressing your question. I would like to remind that this webinar is being recorded, and the recording will be made available as soon as possible on the webinar's webpage. Today's session is also being live streamed on MDPI's YouTube channel. Finally, I would like to present our chair, Professor Dr. Athanasios Loukas, who is Associate Professor of Engineering Hydrology, Water Resources Management and Development in the School of Rural and Surveying Engineering in Greece. He is head of the Department of Transportation and Hydraulic Engineering and the director of the Master Program Water Resources. Professor Dr. Loukas is currently Section Editor-in-Chief of Water, Editor-in-Chief of European Water, and member of the editorial boards of Water Resources Management and Scientific Review Engineering and Environmental Sciences. Thank you very much for accepting to share this webinar. That's it for me. I now hand over the microphone to our chair, and I hope you all enjoy.
Thank you very much, Sarah, for this kind introduction. I would like to say hello, good morning and good afternoon, depending on the time zone that you are in. So let me introduce or say a few words about this webinar. We nowadays that there is a large scientific and political discussion and about climate change. Climate change variations, however, have always impacts on water resources. There are, however, 3 questions, critical questions that should be answered. Is there strong evidence of climate change? How have we learned anything from the past? Is it possible to respond and take adaptation and mitigation measures, and what measures these would be? This webinar, the scope of this webinar is to provide the forum for discussion. And after 3 introductions, 3 speeches from 3 very well-known colleagues. The first colleague, the first invited speaker is Professor Koutsoyiannis, who is a professor of hydrology and analysis of hydrosystems in the School of Civil Engineering at the National Technical University of Athens. He has served as Dean of the School of Civil Engineering, Head of the Department of Water Resources and Environmental Engineering, and Head of the Laboratory of Hydrology and Water Resources Development. He was editor of Hydrological Sciences Journal for 12 years and member of the editorial boards of Hydrology and Earth System Sciences, Journal of Hydrology, Water Resources Research, Hydrology. He has been awarded the International Hydrology Prize, Dulles Medal, in 2014 by the International Association of Hydrological Sciences, UNESCO, and World Meteorological Organization, and the Henri Darcy Medal in 2009 by the European Geosciences Union. His distinctions include the Lawrence Lecture of the American Geophysical Union in 2014, San Francisco, United States of America, and the Union Plenary Lecture of the International Union of Geodesy Geophysics in Melbourne, in Australia, 2011. He has served as Professor of Hydraulics at the Hellenic Army's Postgraduate School of Technical Education of Officers Engineers. He has been visiting academic professor at the Imperial College, Hydrologic Research Center in San Diego, Georgia Institute of Technology in Atlanta, University of Bologna in Italy, and Sapienza University of Rome in Italy. The second invited speaker, is Professor Louis Garrote, who is full professor of hydraulic engineering at the Technical University of Madrid. His research focus is on the application of hydrological and hydraulic models in water resources planning and management, including floods, droughts, environmental constraints, and reservoir operation, with special emphasis on dealing with uncertainties, particularly those connected to global change. His professional record in integrated water resource management includes collaborations with national and international administrations and the private sector in water resource planning, design, and operation of hydraulic structures, dam operating rules and safety, hydropower, and drought and flood risk management. The third invited speaker is Professor Antonio Cancelliere, who is a full professor of hydraulic, maritime structures and hydrology at Catania University. His research has focused primarily on statistical analysis of extreme hydrological events, water resource management under climate change, drought monitoring and forecasting, serving as PAI on several national and international related research projects. So I think we're about to start the webinar, starting with the talk by Professor Koutsoyiannis. Demetris, we have the floor, and you may start your presentation. Thank you very much.
Thank you very much, Athanasios, for your introduction and for the invitation as well. And I would like also to thank the audience. As you see, my presentation is available already online. You can download it and examine it later if you wish. I will speak about the perpetual change in climate and the diachronic ability of humans to adapt to this change, an ability which in the last century has been augmented by modern technology. That's the title of my presentation. But to make it more fun, I also added a subtitle, which is Moreni Kyrios on Voulete Apolese. Perhaps it's difficult for you to discern the Greek title, but anyway, from the verb moreno or the noun moria, we have an English word moron and one other moronity, which I guess you understand. So I give also the Latin version of this ancient Greek proverb, and its translation in English, which is whom God wishes to destroy, he first deprives of reason. So let's think about whom does he deprive of reason. I put this question to make my presentation stronger, and I put to you a dilemma or trilemma to decide whom he does deprive of reason. I offer myself, you see me here, I offer myself as a first alternative. So please consider this alternative and judge what I'm saying. As a second alternative, I have chosen a recent article among the myriads of articles that link climate change with everything bad that happens today or may happen in the future. This is an editorial for the journal Lancet, published a week ago, and it says it connects climate crisis with cancer and stresses the need for urgent action. Okay, I also have a third alternative to choose, whom does he deprive of reason? And this alternative is relating to energy prices in Europe. Of course, you may know that the real wealth of nations and of societies is energy. Most people have forgotten this very simple truth and try to see existential crisis in imaginative scenarios. In my view, those who are interested about existential crisis should focus on energy availability. By the way, yesterday, watching the news, a European officer, I don't remember his name, saying that to deal with the energy problem, this very high prices in the last months, we should meet the energy targets. So I believe this is a reversal of reason. Of course, the elevation of energy prices is relating to climate policies. So let's see on what evidence these policies are based on. So I have the first question here. In terms of the trilemma that I give you plenty of time, and I will try to give hints to you. In the title of the presentation, I highlighted the perpetual attitude of change in climate. So let's see this in more detail. Geosciences and mostly geology combined with astrophysics and paleontology have given some indications about the evolution of Earth. This graph here has the time from now is 4 billion years ago. And here we have several climatic variables. For instance, the solar radiation in the cradle of Earth was much lower, perhaps 25% lower than is today. Yet, there is a paradox that at this time there was liquid water on Earth. And this paradox is known as the faint sun problem, the faint young sun problem. Also, the rotation of the Earth was 70% higher. The CO2 concentration has varied by 4 orders of magnitude, see in this axis here. What remained almost constant was the temperature. You see the graph here. Well, I said almost constant because if we see proxy data for the last 550 years, which is the Phanerozoic. Phanerozoic is again a Greek word meaning visible life. We'll see that the temperature has varied about 10%, which is 35 degrees, from 10 to 35, which is 25 degrees. It's about 10%. The CO2 has varied by 2 orders of magnitude during this year, and most spectacularly, 100 million years ago, the sea level was 300 meters higher than today. And if we go farther in the past, we may reach 600 meters higher than today. But these are proxy data and involve a great deal of uncertainty, both in magnitude and in the timing. So let's see some instrumental data which are more accurate. The longest instrumental data set is that of the nilometer. You see the nilometer here, it's near Cairo, it's in the Ronda Island in Cairo. And it started in the 17th century. In the beginning of this period, just to say a few words about history, Egypt was living a hectic period where the power alternated between the Byzantines, Persians, and Arabs. But during the Arab period, there were systematic measurements of the Nile elevation, water elevation, which lasted until the Ottoman period. From the Ottoman period and later, we have only sporadic measurements. So during this period, which is 849 years long, we have the minimum and the maximum elevation for each year, the blue lines. And we have also plotted in pink the climatic value, which is a rolling 30-year average, a typical climatic scale. You see, for instance, that at about 780 AD, the climatic value was 1 meter. But in the 1120, let's say, that climatic variable value was 4 meters. 4 times more. Right. So we have evidence that climate of Egypt, not of Egypt, actually Nile covers an area of 3 million square kilometers, which is 10% of Africa. It goes south beyond the equator, Lake Virginia. So it is a big area. It reflects the climate of a big area in Africa. Okay, if you don't trust this instrumental record, see also the modern data. In blue here, we have the annual rainfall in Bologna with a record length of 206 years. The red lines represent the climatic values every 30 years. The message is similar. We have long-term variability. If we were in the kindergarten, we refer to this variability as trends. But now we are adults, so we have better descriptions of the long-term variability, and this, for instance, could be made in terms of Hurst-Kolmogorov dynamics. I will not explain this dynamics, but anyway, you may have questions in the end. Our mass media have convinced most of us that the extreme climatic events are due to anthropogenic climate change. A next step, which I imagined when I prepared the presentation, would be to convince us that what we are wrongdoing today may have also an effect in the past. And indeed, this would be a very nice postmodern explanation of what happened in the 1930s in the USA. This is a big drought that affected 2/3 of the country, of the USA, and also Mexico and Canada, and became known as the Dust Bowl because of the tremendous dust clouds that accompanied it, which reached even the east coast of the USA. Okay, that was about the perpetual climate change. Now I will show a few slides relating to this question. Why climate mitigation does not make sense. The immediate reply is the mitigation presupposes prediction, but predicting is a guessing game for fools. This is not from me. This is a quotation from Schwab's and World Economic Forum's book, The Great Reset. You may have read it. I have read it. Interestingly, the most interesting thing is that the book builds upon this full scheme of predicting and mixes COVID-19 pandemic along with climate change in order to advocate the idea of a global Great Reset. In the next slides, I will provide explanation why climatic predictions are irrelevant to reality. And since the workshop is organized by the journal Water, I bypass the temperature. I will not refer to the temperature and speak about the water, starting or focusing on the atmospheric water. The IPCC conjectured that the water vapor amount in the atmosphere would increase and the hydrological cycle would intensify, and triggered by this very strong claim by IPCC, I have myself studied a lot of the huge data sets, and I published by global analysis in the EGU journal Hydrology and Earth System Sciences last year after open review. You see in the slide here, we have the vapor amount through the years using reanalysis data and ground data and satellite data. And you see that the water vapor amount is fluctuating, not increasing monotonically. And this means that IPCC claim is falsified. Most interesting is this graph here, which is for the 21st century. And it is based on satellite data about the presence of water in the atmosphere. Clearly, it shows at all levels, all zones of the atmosphere, it shows that the atmospheric water is decreasing, just the opposite of what IPCC claims. I have to skip several slides because of the limited time, but if you download the presentation or my paper, what I mentioned before, you see some other similar graphs. This graph is for precipitation and evaporation. You see again fluctuations. These similar things for extreme rainfall. For daily precipitation variability, which is in the 21st century has been decreasing, signifying less frequent extremes over the entire globe. Another graph showing showing that we should not trust climatic models. See the departure, for instance, between models. Models predictions are this here, and this is the reality, which has no trend. The model predictions have a trend for precipitation, and there is a big error in the mean. I have also published with several co-authors other papers showing that climate model outputs are irrelevant to reality. One example for the USA here, you see reality, one model, second model, third model. This one is a multi-rejected paper by my former students and myself, showing that the real rainfall extremes in two Mediterranean sites here, you see the reality and what the models say. So there are discrepancies here in terms of extreme rainfall of about 1 order of magnitude. And now the final part of my presentation, which is relating to adaptation. As I noted, the changes in climate is perpetual, and therefore the adaptation to the changing conditions has been also perpetual and hopefully will be perpetual. This slide I reproduce verbatim from a recent presentation by Stephen Koonin with his kind permission. Koonin was Undersecretary of Energy in the USA, or according to the European terminology, we would say Vice Minister, during the presidency of Obama. He says in the title, adaptation will be the dominant response. I would change a little bit, and I would say, instead of will be, I would say has been and hopefully will be. Let's read the slide, which I fully endorse. It is agnostic, it's different to natural versus human-caused changes. It is proportional, adapt more if the change is greater. It is local, does not require global consensus. It is autonomous, it will happen on its own. It is effective, but adaptation is much easier if you are richer. Furthermore, and I have some additional information here, Kounin estimates that even in the case of a terrible increase of 8 degrees Celsius, the economic impact on the global GDP would be less than 15%. Compare now this figure with what happens with the European economy and what will happen, what is discussed now about what I referred before to relating to the energy prices. 15% if we have 8 degrees increase. As I stressed in the previous slide, adaptation has been the dominant response. And in the 20th century, we see the spectacular result of this adaptation. Because in the 20th century, it was combined, adaptation was combined with technology development and strong economies. We have diminished the impacts of natural disasters. See here, 1920s, 1930s, here we have droughts, here we have floods, and compare with what happens today in the most recent decade. And also, the other graph in the bottom shows that natural disasters are responsible for only 0.08% of the total deaths over there. So we have done, I say we, meaning engineers and water professionals, we have done a great job, and we have spectacularly decreased the risk from natural disasters. I will give you one success story relating to Athens, in which I was personally involved 30 years ago. A prolonged drought lasting 7 years shook Athens in the end of the 80s and beginning of the 90s. Athens, you know that it is a dry area and it has a large population, so it has to collect water for a big part of Greece. Before the drought, there were 3 reservoirs, you see here, 1, 2, 3, and during the drought, we constructed 1 more. So here is the historical runoff and rainfall in one of the beds, the catchments, the biggest, which also has the longest record. Up to the late 1980s, we had observed a decreasing trend, which in runoff, which explained by a trend in rainfall as well. But see what happened in 1988 and the coming 7 years. This is the usual, the normal, let's say, average, the red line. And this is the average of these 30 years. More than 200, less than 100. So it's a shocking change. How we handle this situation? We took several measures, of course, and built a proper practical and theoretical framework. In the practical, in terms of practical measures, most important was the close collaboration between the National Technical University of Athens, the Athens Water Supply and Sewage Company, what is called the ETAP, and the Ministry of Environment and Public Works. In terms of theory, we understood that the droughts are regular natural events, not associated with human influences. And based on this, we built a proper modeling framework using stochastic Hurst-Kolmogorov dynamics. We developed a decision support system, which helped to find the correct measures during all these years. But also we had practiced transparency, and we provided veritable information to all population of Athens, and we were able to engage the population in the management of the crisis. We designed and implemented an increasing block rate pricing structure combined with legislation measures for water conservation. And finally, we designed and implemented several technological measures. I will show some. The result overall is that not even in one house, in not even one day through this 7-year period, was there a water supply failure due to the drought. The water consumption of Athens was decreased by 1/3 because of the measures that I mentioned. The new groundwater resources were exploited, and we were able in 1.5 years to build a new tunnel, 30 kilometers long, and divert the river revenues, which I showed before, to Athens. In another 4 years, we were able to build the new dam of Evinos, and thus to increase the water supply from Evinos to Athens. And now Athens has a perfect water supply system. But again, there can be another drought in the future. So as most of us prefer to speak about scenarios, I offer one. What will happen in the next drought in Athens if it is bigger than this one? The drought, of course, will be attributed to the anthropogenic climate change. It will be managed by the newly established in Greece Ministry of Climate Crisis. I don't know if you have such ministries in your countries. We are an example. Climate modelers will be appointed to... Yes?
I don't want to interrupt you, but you have to come to a conclusion because we're running out of time.
Can you give me 1 minute?
Yes.
Okay.
Yes.
Okay. Of course, climate modelers will appoint it, and the urgent measures to immediately shut down the lignite power stations will be taken, etc. Okay, we also studied alternative approaches in addition to what I referred, which were rejected. For instance, we studied, and this is a publication to the Journal of Hydrometeorology, we studied what the climate models say, and we decided that they are dangerous because they give a very stable future while the actual uncertainty is that high. We also studied this trend approach, which as I said, is for kindergarten. And we decided that this is also nonsense. And our decision is verified. Now we have this data here. When we were living during the drought, we had data up to here. Now we have also this, and we know that, for instance, all 3 reservoirs spilled in 2006, and again 2 of them in 2020 and 2021. And that's it. So my concluding remarks is this: change is nature's style. It occurs at all time scales. Change is unpredictable. Here I borrow something from Winston Churchill. The future is unknowable, but the past should give us hope. In the past, adaptation has been the human's response to change. If we return to reason, this will also be the case in the future. Technology has augmented the human ability for adaptation. The results have been spectacular in the last century. And of course, human adaptation requires human intelligence. On the contrary, morality results in devastation. Thank you.
Thank you very much, Demetris, for the intriguing presentation. And I should mention that we'll have discussions at the end of the 3 presentations. Now we are moving to the second invited speaker, Professor Louis Garrote. Louis, You have the floor.
Thank you, Athanasios. Let me share my screen. Thank you again for the introduction. Also, thank you, Demetris, for this very nice presentation, which is a very good introduction to which I'm going to talk about. Because I was planning to talk about adaptation and basically to discuss one adaptation strategy, which is very simple and very obvious, which is in order to face water scarcity, we build reservoirs to store water. This is a very simple method of adapting. And I hope to show you that this is a method that can work very well in these conditions. So I'm going to talk about three things. First, make a distinction between runoff and water availability, because the focus of the talk will be water availability. Then I will briefly discuss projections of water availability that, as the previous presentation said, are really confusing and do not really send a usable message to act on the future. And finally, I will discuss the role of adaptation, specifically on water availability. Well, usually in climate change analysis, we use runoff as a proxy for changes in water availability. So there are many studies that they analyze changes in mean annual runoff and conclude that those changes will be directly translated into changes in water availability. But we, of course, know that this is not the case, because in regions where water is scarce, water availability is not really provided by mean annual runoff, but mostly by human infrastructure, the infrastructure that we build to use water. Mostly flow regulation. We build waters in order to build reservoirs in order to be able to store water and be able to use it in the periods where natural runoff is not enough. So there's a whole full theory of reservoir storage that is currently being a bit neglected, I have to say, and can be very useful to make analysis regarding climate change. Of course, there are also other factors that make the analysis more complicated, like changes in variability in addition to changes in mean annual runoff. And also the way we use water is really decisive. The way, the kind of demand, the reliability that is required, how much water we allocate to environmental flows, etc. All these things are important. So in order to focus the talk, I would like to share with you my definition of water availability, which is related to blue water availability. That is water in the rivers, not groundwater, mostly surface water that is available in rivers. So I would say that water availability can be defined as the maximum demand that could be supplied at a given point in a river network, which is the abstraction point, using the available storage, if there is any, with realistic management, in applying the usual operating rules for these reservoirs present in the system, respecting the water allocation to environmental flow, and considering the proper monthly distribution of demands, which is different if we are thinking of irrigation than if we are thinking, for instance, in water supply for urban consumption. And of course, considering the required reliability criteria that is usually applied to each of the demand present in the system, which required reliability is not the same for urban consumption as it is for irrigation. So all these factors together are probably too many, but they all have to be taken into account if we want to make a good projection of water availability. Now, the problem is that different assumptions in these factors can lead to very different results. So we have to state our assumptions very clearly in order to be able to interpret the results. One thing important in reservoir storage is that variability is critical, both seasonal variability and interannual variability. So if we live in a region with low hydrologic variability, we are likely to be able to supply our demand using directly the water is running in the river without having to build storage, because the variability is low, and therefore there is good reliability for the supply, even if we don't build storage. But in areas with high hydrologic variability, with aridity, with water scarcity, we require storage in order to be able to satisfy our demands to a certain point. So with the same conditions, same mean annual flow in a river, if we are in a region where there is high variability, in order to supply the same demand with the same conditions, we will probably have to build reservoirs if we are, as I said, located in a region exposed to hydrologic variability. So variability is really important. And there is also another important thing, which is the nature of change. So let's think that we have a time series, say, of river flow over time, and we are expecting to change, either due to natural variability or to climate change or whatever. There are like two modes of change that we can describe. First would be a step change in which the mean gets changed. For instance, we experience a reduction in the mean, but the variability stays the same. It's like we reduce all the values by a constant factor. That would lead to a new time series with less mean, but with the same standard deviation. And therefore, since the mean is less than before and the standard deviation remains the same, we would expect a greater coefficient of variation if we experience this type of change. Now, there's other possibility which is usually applied in climate change analysis due to the delta method, in which we specify the changes as a fraction of current values, and that would be proportional change, in which we multiply all the values of the original time series by a constant. If that constant is less than 1, we get a reduction in the mean, but we also get a reduction in variability. If this proportional change is in place, we would expect to see the same coefficient of variation, because the standard deviation is reduced exactly in the same way as the mean is reduced. So these are like two streams of change, and it's interesting to distinguish whether we are facing a step change or a proportional change when we are analyzing reducing available flows. Now, we built a model to do this type of analysis in an automatic way, and it had to be a simple model because we want to apply it over the large scale, over regional or continental, even continental scale. So we'll build a model based on geographical data, which includes rivers and existing reservoirs. Those are the main ingredients of the model. And with that model, we apply an algorithm that combines a set of reservoirs to supply a demand in a given point, and trying to maximize water availability. So the management rules are defined in order to maximize water availability. This model can be used to estimate the potential water availability at any point in the river network, according to the assumptions that describe the seasonal distribution of demand, the required reliability, the storage available, etc. All the parameters that describe this type of models. And we've used this model, we've applied this with all, not all, because that's impossible, but with a very large amount of climate projections coming from different emission scenarios. This is probably unorthodox to mix emission scenarios coming from different sources, the A1, A2, B2, and the more recent RCP2X scenarios, but we put them all together just to find out what the range of future projections would be. And by analyzing these scenarios, first thing that we notice, as Demetris said in the previous presentation, is that it is absolutely necessary to correct for bias, because climate models show a very large bias, so we have to correct for bias. And also that all of them tend to agree and project a significant reduction of runoff in Southern Europe. Most of them produce very relevant reductions, and there are very few that produce increases of runoff. So one thing that is interesting is that if you compare the projections of runoff, the changes in runoff versus the changes in local availability, the availability that can be obtained in each subbasin, they look very different because projections in runoff are relatively smooth, but changes in local availability are more irregular. They depend on the amount of storage that is available locally and also the hydrological regime, etc. But they depend on several factors. So what we did was to accumulate all local water availability along the rivers in order to obtain projections of river water availability and compare them to projections in river runoff. Yeah, as you can see now, the differences are not so dramatic, but there are still big differences between the expected change in runoff and the expected change in water availability. We are looping here over 5 different models that can show you, because the image between each 2 pictures is changing a lot. That means that there is a lot of model uncertainty. But if you compare the results of all models under different emission scenarios, you realize that there's also a big uncertainty related to regarding emission scenarios. So the idea is that there is a big uncertainty. There is many things that could possibly happen. And of course, although prediction is very different, is very difficult, I guess one of these at least must be true, because there are so many of them are so different that at least some of them can be true. This is the general idea, the general study for Europe. We did a more focused study on Southern Europe, in Mediterranean Europe, and we focused on 16 characteristic basins. If you plot the mean annual flow in the horizontal axis versus the storage expressed as a fraction of mean annual flow, you realize that areas with high annual runoff require, as I said at the beginning, require very little storage, but areas with high variability and low annual runoff require much higher storage. And this is the distribution of storage availability across Southern Europe. So we took representative basins of all these regions. The basins are shown on the right, and they are ordered from lowest storage available to highest storage available. And we did this type, the classical analysis in climate change. One is to analyze climate projections, and I'm showing the example for the Ebro Basin, but we did the analysis for all of them. So we plotted the expected change, unit change in mean annual flow versus the expected change in coefficient of variation. Like if there was a step change, we would expect no change in coefficient of variation. As you can see, the change in coefficient of variation is very large, and it's actually increasing. So it means that it is unlikely that the type of change that we can expect is of the step type. If we plot the results for all the basins together, this is the picture that we get that shows the global vision for the entire region. On the left, you have changes in mean annual flow versus changes in coefficient of variation. And on the right, I've shown changes in mean annual flow versus changes in standard deviation. Remember, in the case of a step change, we would expect no change in coefficient of variation. And in the case of proportional change, we would expect no change in standard deviation. And the fact, we observe that the projections show changes in both variables, an increase in the coefficient of variation and a reduction in standard deviation. It means that we are probably somewhere between the step change and the proportional change. We can also see that for basins with high reservoir storage, which are shown in warm columns, the expected changes are more extreme than in the case of climatic regions that require low storage. So it means that probably the projections show a worse picture for areas that are already exposed to water scarcity. If we study potential water availability, we decided to plot it this way, in which we compute potential water availability for all basins under all emission scenarios that were analyzed, and plotted it as a sort of a probability distribution, or a rank sort distribution, if you like. The plot on the left corresponds to the climate change scenario, the future scenario, and the plot on the right corresponds to the distribution of water availability for the reference condition. And there is a strong model uncertainty, and that is why we don't get one single value for the reference condition. If you compare the results obtained in all 16 basins, you will see first that water availability is clearly sorted as a function of, while expressed in terms of mean annual flow, is sorted as a function of reservoir storage. Basins with larger reservoir storage are able to produce a water availability which is closer to mean annual flow than in basins with low reservoir storage, even if those basins have lower variability. And it is also apparent that the changes are very dramatic, that there will be a big shift in the distribution of water availability as described by climate projections, compared to the distribution of water availability as described by the control scenario. This means that there will be strong reductions in water availability. One thing that you can do is plot water availability, changes in mean annual flow versus changes in potential water availability, and see how they compare. For the entire region, we found this type of plot, which is a bit contradicting to the first thing that I said in the presentation, which I said that changes in mean annual flow are not the same as changes in water availability. In fact, this picture seems to imply that changes in annual flow are actually a good proxy for changes in water availability. But there is a trick here, which is the role of reservoirs. This is the case because we have big reservoir storage in areas where water scarcity is extreme, is very large. And that tends to attenuate the effect of changes in mean annual flow. If we did not have the available reservoir storage, most likely the changes in runoff will be multiplied in terms of water availability, because as we saw, there is also a significant increase in the coefficient of variation in the time series. We made this hypothesis and tested it by a sensitivity analysis, in which we took the currently available storage in each of the basins and changed it by increasing and reducing it, and repeating all the computations and plotting the results that we got. We used two indices. One we call the attenuation index, which we are showing on the left, and the other one we call the uncertainty index, which is shown on the right. And for the attenuation index, we found that the reservoir storage indeed attenuates the effect of changes in runoff, the effect of reductions in runoff, so that you don't get such a wide spread of changes in water availability as changes in runoff occur. Regarding uncertainty, we also found that the presence of reservoir storage in the basin reduces the uncertainty, which is also good for making decisions. It's much easier to make decisions with low uncertainty than it is to make decisions under big uncertainty. Okay, so this is the projection. Just to finalize, I would like to say a bit about adaptation. We saw that we can expect strong reductions of runoff and water availability if climate projections are true, but there is one clear message. Policy and management through adaptation can modify availability, and that is what we've been doing all the time. In fact, we are already experiencing changes in runoff, and we are already adapting to those changes. We don't stay put and don't do anything when there are changes in the boundary conditions. We adapt to that. In order to prove that, we wanted to do an analysis of what could be the effect of certain policies or certain adaptation behavior in terms of water availability. And we explored two types of adaptation options. One is like public adaptation, in which you operate the system in a better or more efficient way. For instance, you build basin interconnections, you densify the distribution network, so you improve the way you operate your infrastructure. And that would be one adaptation path that can be very effective for water management. And the other adaptation path is more individual, and we call it governance, because what we mean is that we can enhance the legal framework for water sharing, so that if we build capacity so that water users can improve the way they use water, and they build some tolerance to water deficit through other measures, you can accept a lower reliability, and that will increase the water availability. So we did an analysis with the model to see the effect of implementing this type of adaptation options. And as you can see here, by comparing the two situations, the pre-existing without adaptation and the situation with adaptation, we can reduce by a lot the projected water deficits in entire Europe. And if you analyze individual basins, for instance, these are a few examples from basins in Spain, the actual water availability is the projection of water availability is the black lines, and the projections of water availability under adaptation conditions are the colored lines. We don't need to get into the details, but we can clearly see that by improving adaptation, we can improve our water availability to a much larger extent than the reduction that is expected due to climate change. So this means that adaptation is a good pathway to prepare for climate change in terms of water management. We did a more elaborate analysis in terms of water availability for irrigation by specifying different policy measures. And just so that you can understand this picture, in each graph, the green vertical line shows the expected reduction of irrigation demand that will be required to keep the same level of reliability under climate projections. And the colored lines, the green, the blue, and the red lines are the reductions that you can change, or not the reduction, the changes that you can obtain by implementing several public policies. The blue line is by increasing reservoir storage. The green line corresponds to increasing or changing, increasing or reducing the allocation to environmental flows. And the red lines correspond to improving water use efficiency in urban use, like what Demetris said that was done in Athens during the drought, that water efficiency was increased by 1/3. By implementing these measures in the basins, as you can see, you can, in some basins, which are shown on the top row, these large basins of Spain, there is still potential for increasing water availability through different measures, and you can compensate for the expected reduction in water availability for irrigation. Whereas in the basins shown in the lower row, the potential for increasing availability through reservoir storage is really limited, because those basins already have a large reservoir storage available. I can see Athanasios that is going to tell me that I have to conclude, so let's conclude. 3 ideas. One is that the modeling tools can be useful to do this type of analysis, but we have to extreme our care while doing the estimation of changes in water availability to specify exactly the assumptions that we are doing in our analysis. Second idea about water availability projections, they are usually very pessimistic, but they cover a very, very wide range. So that is very difficult for policymakers to determine their plans based on that, and usually leads to extreme restrictions of water availability that will not be beneficial for society because they will probably prevent some potential developments to being implemented. And finally, the third idea is the adaptation is very important. And I would say that the capacity for doing things through adaptation in water management is much larger than the expected changes that will be due to climate change, except perhaps in very localized areas where the conditions are already very extreme. But our potential for adaptation is much larger than the threat of climate change in terms of quantitative water availability. So I leave it here, just a few papers in the Water Journal that you can check if you want further information about all these topics, because they describe this type of analysis in detail. Thanks a lot.
Thank you very much, Louis, for this very interesting presentation linking the water availability with the variation of surface runoff and the water storage systems, reservoirs, and so on. Now we have the third invited speaker, Professor Cancelliere. So Antonio, please, you do have the floor.
Thank you. Thank you, Sakis, for organizing this very nice webinar. Unfortunately, I hope that in the near future, we will be able to organize something similar in presence, of course. So the title of my presentation is Droughts, Climate Change, and Water Resource Management in Mediterranean Areas. And unfortunately, I will not provide answers, but mostly questions. So I'm sorry about that. But first of all, let me start with some a tribute to our host, Professor Loukas. This is taken from an ancient Greek comedy by Aristophanes, that's Clouds. And this was first performed is 423 before Christ, so some 2,500 years ago. And I think it synthesizes very well what is the role of water engineers in dealing with floods and droughts, and more generally with natural disasters. And in this comedy, the chorus goes, then we will act as guardians for all your crops and all your vines, making sure that they are never harmed by drought or by a drenching rain. Now, of course, at that time, climate change was not around yet, so they couldn't blame climate change for natural disasters. They would blame the deities, of course, but nonetheless, I think this synthesizes very well what our role should be. And the other thing is this was taken from last week newspaper, local newspaper here. I'm talking from Sicily, Italy, and apparently in Sicily they've been able to grow coffee for the first time. So it looks like that Sicily is becoming kind of a tropical country, and we have entered the coffee belt. And now, of course, if you read the article, they will say that this is due to climate change and all that. But my idea is that probably improved agricultural practices may have also played a major role in this. So, but let's go to the topic and let's talk about droughts. Now, droughts is a very, very tricky subject, actually. Droughts are very elusive phenomenon to analyze. And unlike other extreme events, it's very difficult to define and characterize. We would all agree about what a flooding is, when a flooding starts, when a flooding ends, but it would be very difficult to find an agreement about defining droughts. and even identifying objectively when it begins, when it ends. And of course, the complexity of droughts stems from the fact that droughts affect all the components of the hydrological cycle. And one distinction that we often make is between meteorological droughts, agricultural drought, hydrological drought, and water resource drought. So meteorological drought is just precipitation deficit. And as this precipitation deficit propagates within the different components of the hydrological cycle, other deficit will arise, like in terms of soil storage, of surface water storage, and then we will have deficit in our water supply systems. And at the end of this process, we will have economic, social, and environmental impacts. Now, the problem is that, of course, that there is a large delay between this precipitation deficit and this economic, social, and environmental impacts, which is actually when we perceive drought as such. So this partially explains why it is so complicated to define drought or to come up with a universally accepted definition of droughts. Now, if we talk about potential changes in hydrological cycle, of course, what are the changes that might affect droughts? Well, first of all, changes in precipitation patterns certainly will affect meteorological drought. If we have changes in atmospheric evaporative demands or evapotranspiration, this will affect soil storage, soil water storage. Land use changes might affect surface water storage and groundwater storage, of course, and water deficit in water supply systems may be affected by changes in water demands. So there are all kinds of changes that may enter into play when we are looking at droughts. And droughts, there are hundreds of indices and indicators that have been developed in literature to identify droughts and assess its characteristics. And the interesting thing is that we end up defining droughts in terms of the index and not the other way around as it should be. And this is just another proof that defining drought can be very, very complicated. Now, this is a quick search that I did this morning about droughts, entering keywords, droughts and climate change in the water portal, the water journal portal, and 98 results came up from 2011 up to date, which is about 10 papers per year have been published with these keywords, and this is just water. So this is an indication, of course, of the great interest about droughts, about the possibility that drought characteristics are changing in time. So the problem with the literature is that there are very disparate results. So this is just an example, and it's kind of funny actually, because these are basically two contemporaneous papers that came out in 2012, and this is Nature Climate Change, and this is Nature. And if you look at the titles, increasing drought under global warming in observations and models, it seems like the droughts are going to change. And the other one says little change in global drought over the past 60 years. So two completely opposite patterns. If we look at more recent literature, and if we analyze, for instance, Western Europe, there is this paper where they analyzed the long series between 1851 and 2018 by Vicente Serrano and others. And their conclusion is that the trends in droughts over Western Europe are statistically not significant from a long-term perspective. So it looks like droughts are not changed. Another paper by Spinoni and others conclude that at a global level, droughts have not changed, but there are some hotspots that might have experienced changes in drought frequency and severity, and in particular Patagonia, the Mediterranean region, Sahel, Congo River, and other things. So The other thing is that most of these papers are based on traditional indices. I will talk about indices in a moment. There are some exceptions. There is this paper by that's been published in Water, where they actually developed a kind of more vegetation-oriented type of index to analyze droughts. And then there is the question of attribution. You know, even if there is, even if we find some changes in our historical droughts, can we attribute these changes to human-induced climate change? And this is an analysis of 170 studies that examined the role of human-induced climate change. And if you look at this, I mean, in red bars, it indicates that that there is a kind of concordance about the fact that there is human that the changes can be attributed to human-induced climate change. So, for instance, for heat, of course, there is a kind of a relatively large agreement. But if we look at other events like droughts or even rain or cold ice, snow, if we look at drought, for instance, we see that roughly out of the something more than 40 droughts that have been investigated, only 50%, for only 50%, we can potentially attribute them to climate change. And for the rest, either we have to go in the other direction or we have inconclusive data. So the bottom line is that we still don't have clear evidence of changes in droughts, either due to climate change or other factors. And this is actually reflected even in the 6th IPCC report, where the conclusion is that there is low confidence that human influence has affected trends in meteorological droughts. There are some areas where this confidence is a little higher, but if you see here, this is kind of a typical map of IPCC. This is the Americas, of course, Europe, Africa, Asia, and Australia. And you see that the white spots, which is low agreement in the type of change, are basically the majority worldwide. But if we take a look at the Mediterranean area, there is some medium confidence that they've actually increased. Now, why this contrasting conclusions? Well, people have tried to understand. Some people have addressed the problem of atmospheric evaporative demand on drought and its response to climate change. And certainly atmospheric evaporative demand is a very important factor when it comes to drought, because obviously there is a feedback mechanism with moisture, and so as drought develops in time, we can expect that the evaporative demand from the atmosphere, what we would call in the old days potential evapotranspiration, this will obviously increase. And the problem is that these feedbacks are still not completely understood, but they play a major role in drought and drought analysis. Now, to go back to the indices, there are many indices around, perhaps too many, and they differ for the different variable taken into account. What they do, they generally measure negative deviation of a hydrological variable or of a proxy of another hydrological variable with respect to some normal level. Now, what this normal level, of course, it's a problem within the problem, because it's not easy to define. And then we characterize droughts in terms of duration, severity, intensity. Often we make use of run theory. And of course, if we have a non-stationary or a changing setting, This, of course, poses some questions. So what is normal condition? How do we define normal conditions if the conditions are changing by definition? How do we standardize condition among different times, and how do we take into account the presence of trends, shifts, and cycles? Now, these are, I think, still open problems that have been only marginally addressed by the present literature. One thing that I would like to show is some analysis about this standardized indices that have gained great popularity. For instance, standardized precipitation index is probably the most famous of all, or the SPEI is another index that has gained popularity. The way these indices are built is through an apparently complex mechanism, but really, if we look at it, it's in essence they are very simple. What we do is basically we start from a series, say in this case monthly precipitation, if we want to build a standardized precipitation index, and we aggregate values in the last k months. Then we transform these aggregated values into a non-exceedance probability by means of a probability distribution. Generally, gamma is adopted, but of course, this is just a detail. And then we transform this non-exceedance probability into the corresponding standard normal variable. This would be kind of the mathematical notation for this operation. And it looks like that there is some magic involved, but really, to really understand what we are really doing, let's assume that this aggregated process is normally distributed. If the aggregated process is normally distributed, instead of having a gamma distribution, we would have a normal distribution here. And then when we go back into a standard normal distribution, at the end of the day, our SPI would be just the value of the aggregated hydrological variable minus the mean divided by the standard deviation, which is the way we would normally standardize from a statistical standpoint. So all we are doing, we are just subtracting the mean and dividing by the standard deviation. Of course, if the distribution is different, we are doing, there might be slight differences, but essentially this is what we are doing. But the important thing that I would like to point out is that the index, since the index is based on this accumulated process, and then we compute the index every month, we keep going one month after the other, the index will be basically structured as a moving average process. And this moving average nature of the index obviously will imply that the series will exhibit, first of all, a very strong autocorrelation structure, and this autocorrelation structure will be stronger as k increases, and also will exhibit apparent cycles, shifts, local trends, all kind of strange thing will start to emerge. Now, from a stochastic point of view, we can show that actually the SPI is structured as a periodic moving average process, and if it is if aggregated precipitation exhibits some correlation, it will also be Palma. So we can derive stochastically the properties, the theoretical properties of the indices. But the important thing again is that these indices will exhibit a very strong autocorrelation. What does it mean? Well, it means that this is an example of application of computation of SPI to this average precipitation Simeto watershed at Barca. This is the largest watershed in Sicily. So if we start with we take this average precipitation and we compute the SPI at 3 months. This is the series that we have. Then if we compute the SPI at 12 months, it means that every month we take the aggregated values in the past 12 months. We will have this series here, 24 months, 48 months, and so on and so forth. And you see that as the time scale increases, obviously, all we are doing is just a moving average operation. we have all these apparent shifts, apparent trends, local trends, apparent cycles that arise. So, you know, if I look at this series, well, this series, I might read so many things about the changes that supposedly are occurring in my watershed. But in reality, this is just only apparent. There is a theorem due by Slutsky, which was published in 1937, and this theorem was later analyzed by Moran and more recently by Klemesh and Klemesh. The late Witt Klemesh wrote this paper with his son Ivo. And basically what Slutsky theorem says is that if you start with a purely random process, so random process means it's fully stationary, no cycles, no trends, no shifts, nothing, and you start applying some kind of moving average process to it or cumulative processes to it, as you apply repeatedly moving average or cumulative process to this random noise, the result will be asymptotically a sine wave, regardless of the fact that initially your series was absolutely random. So these are some examples taken from Klemesh paper. It started from series, from streamflow series from 4 streams in Europe. And if we start applying moving average, there is some cycles that starts to appear. Of course, if we apply again moving average operator, these cycles becomes even stronger. And at the 4th time, we get a sinusoid. So what this means is that basically this behavior that we are reading in our SPI series as the aggregation time scale gets larger, it's just apparent. It's not something that is inherent in our series. So it has, I wouldn't say it has no meaning, but certainly it requires careful analysis before concluding that we have a downward trend or we have shifts or different things. And this, of course, is reflected if we apply Mann-Kendall test, assuming that we are kids, as Demetris was saying. And so if we apply Mann-Kendall test in the series at 3 months, the trend is absolutely not significant, but as the time scale increases, we get a p-value that gets smaller and smaller. So eventually at 24 months, we have a statistically significant trend, and at 48 months, an even more significant trend, although the original series, of course, did not exhibit any trend. Now, there are some statistical tools out there to deal with the autocorrelation, but when you want to analyze trends, but I have to say that unfortunately, people still play the game of doing some trend analysis on SPI series without taking in consideration these problems. And the other thing is what about the future? Of course, you know, because if we look at the past, there is no strong evidence. What about the future? Well, the future, of course, prediction is very difficult, especially about the future. It's a statement attributed to Niels Bohr, and what do we do to assess, to evaluate what's going to happen in the future? Well, we resort to climatic models, of course. But the question is, do climatic models reproduce well the present climate? And we already saw, Demetris showed something where he already pointed out that quite often they do a very, very bad job at reproducing current climate. Here we try to do some kind of more systematic analysis. And we started from observed series, 84 temperature stations, 335 precipitation stations, distributed in southern Italy, Sicily and Calabria. And then we analyzed 19 combination of GCM and RCM models. And we repeated this for the whole area and also for 6 climatic zones identified by means of principal component analysis. And the result is very discomforting, I have to say. Just looking at air temperature, if we look at air temperature, now these are box plots of the difference between the mean annual temperature at each station and the corresponding mean annual temperature reproduced by the models. Now here we have the different models are here, and you can see that in terms of even just by looking at the median of the error that these models have in reproducing temperature, we have errors that are by far larger than the, typically people would say if there is an increase of 1.5 degrees, very terrible things will happen and so on and so forth. But this model are not able to reproduce the current climate already. And of course, the answer to this will be yes, but we are going to apply some kind of bias correction. So we will certainly fix things. It's true, but on the other hand, one may argue that these are supposedly physically based models, and if there is such a large amount of bias into a physical model, that presumably it has some inherent nonlinearities involved. How will this errors in precipitation will propagate to all the other components involved? So this is kind of discomforting. This is not new, of course. The authors have already played this kind of game for different regions of the world. If we look at precipitation, we get this type of behavior. Things seems to be a little better, at least from a median perspective. And we also analyze the drought characteristics, and for instance, we find that models generally tend to underestimate the maximum intensity of droughts. And these are also errors in terms of return periods for fixed drought land. But at the end of this, what we did was we made some kind of ranking of the different models. We basically used this statistics to make some ranking. Now, the idea of this ranking, of course, is not just to say which model is right and which model is wrong, but it's presumably, I think, that this can give some guidance when we have to select the model that we want to apply for our analysis. Because what people do generally is they take all these models, then they do some kind of ensemble approach. So basically they take the average results, but of course average can be a very, very bad estimate of what's going on, and it's not always true that positive error compensate with negative errors, and so at the end you have the right result. So for instance, based on this ranking, when we played the usual game of assessing future impacts of climate change on a water supply system in Sicily, where we applied the usual modeling cascade, starting from our GCM, RCM, precipitation and temperature. Then we estimated runoff, and then we applied a simulation model for the reservoir in order to assess the impacts. And so these are just the differences in the estimated hydrological variables. And what you get at the end is this type of plots that are very similar to what Louis was showing, where you can compute the temporal reliability and for different scenarios based on different demand levels and different storages. And one interesting thing regarding to adaptation, of course, I agree with Louis when he says, and I've come to my conclusion. I agree with Louis and Demetris when they say that, of course, adaptation is the key, but building new reservoirs in particular is a good thing. I must say that right now we are involved in a hydrological study for building a new reservoir in the Simeto watershed, and I must say that we are also doing this kind of game of assessing the impacts of climate change on the system. And I have to say that this type of reasoning works very well with politicians. I mean, politicians are kind of very sensible to this. And apparently, when you do your analysis based on observed data, they are not too excited. When you show them that very terrible things will happen in the future, they are very happy to hear that, and maybe they are more willing to actually do something to adapt to water scarcity, actually. So I think that one way of, perhaps we as water managers, we should use climate change as a leverage to implement all the adaptation strategies that are necessary regardless of climate change. I think that's my idea. So these are my conclusive remarks. These are just a synthesis, and just to say that preliminary screening of GCM, RCM models can help to reduce uncertainty, or perhaps, unfortunately, lose confidence in them. Thank you very much.
Thank you very much, Antonio, for a very interesting presentation linking the drought phenomenon with climate change and possible adaptation measures. I think now we are ready to start the discussion and the questions from the audience.
It says, just wanting to get some clarification on water availability definition by the second presenter, so it's for Louis. By excluding groundwater, but surface water, when we all know that there is always that interaction between the two.
Yeah, well, thank you for the question. It's much harder to answer than it looks. The easy way out would be to say that we focus only on surface water availability because we don't have modeling tools for groundwater, and that is what really happened. We don't have a similar model to account for changes in groundwater availability. But the difficult part is that when there is water scarcity, surface and groundwater are inextricably linked. Why? Because as you start pumping groundwater from the aquifer, the water table gets depleted, and that affects the base flow runoff from the rivers. And therefore, your stream flow series also changes. So if you want to account for current groundwater exploitation, you should account into that the effect that it has on surface water, not only on surface water availability, but also on, to say, sort of natural surface water under natural conditions, not really natural, but without reservoirs. Just to summarize, doing the joint analysis is not easy at this large continental scale. It can be done, and it has been done in specific cases in basins where you can characterize the aquifers and the pumping rates. And of course, you can increase water availability a lot by implementing conjunctive use of surface and groundwater. But at this continental scale, at least I don't know how to do it. What we have done in the past is to account for surface water availability on one hand, and on the other hand, for groundwater availability, but disconnected, not interlinked, because linking them is very, very, very hard, at least for me.
Okay, thank you, Louis. There is a comment for Professor Koutsoyiannis by Ricardo Mantilla. Dr. Koutsoyiannis, thank you for a very informative and provocative presentation. You made a mention about the impact on climate change on GDP. I want to point first that disasters contribute to GDP. Recovery activates local economies. So I wanted you to comment on how that plays in your message. Thank you.
Yeah, that's a very interesting remark. Yes, it can be like this. I'm not a specialist in economics, of course, and what I believe is that when we are an organized society, we can rebuild what is damaged from natural disasters. And this also needs to have technology and intelligence and strong economy. May I also mention that I believe that in Europe and in the US, there is a problem in terms of using technology and most importantly, reason. Because in my presentation, I gave several examples to show or to provoke the idea that currently we have some departure from reason. So, yes, in short, my answer is yes, we can even increase GDP by disasters, and history has proven that. But in order to do this, we need a good organization and a good relationship with the reason. And since I mentioned Athens, I would like to say Athens is, to repeat, Athens is a very dry place and used to be a dry place even in the antiquity. And it is Athens where hydraulics were first developed. We have from 600 BC, we have an aqueduct. It's very close, actually, in my university here, and it is very close to where I'm staying now. And this aqueduct still operates until today. So, because it was drought, there was development. And this is very well explained by Thukydides, but I'm not going to say the details about that. So I think for the remark, I'm not well prepared because of lack of knowledge in economics to reply, but I gave some hints.
Okay, thank you, Demetris. I have a question, a general question that applies to all of you by Professor Garrote. I wonder if we can save the biodiversity and protect the ecology of intermittent rivers and ephemeral streams. Is there enough knowledge in that subject? Do you want to comment on or answer to that?
Well, I can go ahead and comment on that. I don't have an answer to this,
yes.
but I think that there is more knowledge than it used to be. But there is still a long way to go before we can really understand the anthropic effects on the natural ecosystem. And this is one of the most urgent tasks in science, to be able to do things in nature without having to cope with unwanted adverse effects. But of course, especially in this type of ecosystems, in intermittent rivers, it's very difficult to figure out what's going on. And we don't really have a clear management practices that would protect the ecosystem with respect, for instance, to water abstractions. You know, we are now in Spain in the phase of implementation of ecological flows throughout the country, and we face the challenge that there are many rivers in Spain that are intermittent. Some of them every single year, and others, they are just intermittent every 10, every 20, every 50 years, they just dry out. And we don't really know how to establish an ecological flow regime for those rivers that would keep the natural environment as what they are, which is intermittent rivers. We can specify ecological flows, and if we have storage upstream, we can supply that ecological flow in a constant way, but that would change the nature of the ecosystem. So I agree that this is a challenge, and there's still a lot of work to be done before we can act on these type of rivers with full knowledge of the implications of what we are doing there to abstract water.
May I add something?
Yes, yeah. Yes, Demetris, yes, please.
Yeah, just I wanted to connect Louis' reply, which I agree with the example that I used in my presentation with the Athens water supply system. The old reservoir of Mornos, which was built in the 80s, did not have an ecological flow, an ecological diversion for the area. So below the dam, downstream of the dam, there was no water at all. Now, the new dam that we built in Evenos was modern. We implemented, we studied and implemented an ecological flow. And of course, this is a big improvement. I think that ecologists have provided good service to water professionals, because they gave us ideas. They show how significant is the problem, and I believe we have resolved partly this one. Of course, there are other issues like the floods, which are not covered by the ecological flow. A dam stops the floods, but again, there are solutions like making artificial floods in order to be closer to the natural regime. So there are several solutions the technology can provide, but again, this means some intelligence and some collaboration in the society, some scientific approach rather than ideological approach to the problems.
And if I may,
yes, Antonio, please. Yes.
Some experiences that we are currently undertaking in Italy, and particularly in Sicily, we have recently adopted an ecological flow directive that actually imposes ecological flows downstream to any diversion structure. Now, of course, although this is in principle very easy to apply if you have a new diversion, because for instance, as I said before, we are currently working on the preliminary design of a new reservoir, which is about 40 million cubic meters. And then of course, if you want to build a new diversion structure, you can basically take into account the ecological flow as a kind of a demand for your you could look at it as a demand to your diversion structure, or you could look at it as a reduced runoff for your diversion structure. So it's not a big problem. But the problem is that when you want to apply the same methodology and the same ideas to existing structures. Now, I was talking about the Pozzillo Reservoir. Pozzillo Reservoir was built, started its operation in 1959, and basically it has not dropped one water in the river downstream since then. And now there is this ecological flow directive that says that you have to, release ecological flows. So the question is what is the ecological status of the river that we should take into account? The present one, because if we want to preserve the present one, then we should not release anything, because if we start releasing discharges, we're going to change the ecological status of the current river. Should we go back to 1959 and try to restore what was going on in 1959? I mean, obviously it doesn't make sense. We could go even go much back in time, where we had there are archaeological evidences that the ancient Greek would be able to navigate rivers in Sicily that now are completely dry. So what should we do? Should we restore navigation capabilities for our reservoir? Now, of course, this is a joke, but the problem still remains. What is the reference ecological status that we should assume for a river reach where a diversion structure is already there? And I'm afraid that our ecological flow directive does a pretty good job for new diversion, but regarding existing diversion structures, it is. I mean, there is still a large margin of improvement, actually.
Okay, thank you all for answering your commenting this question.
There are some more questions in the.
Yes. This is why I'm pushing on. There is. I'll go to the questions first, and the questions posed on the chat then. So the questions. For the questions, there is a comment question by David Perez. I think it's general and applies to the three of you. Huge amounts of EU research funds are addressed to study climate change. Given the uncertainty related to climate change, do you think that the funds are too much, and that a certain proportion may be addressed to other water management issues? Which ones? Who wants to comment and answer? Yes, Demetris. Demetris?
Yeah, that's a very interesting comment and question. I believe, yes, I agree that the amount that the EU gives to climate research is huge. I would say that this is not the way of doing research, actually. The politicians decide where the research funds should go. I believe there should be some freedom in the academics about what they think is important to research. So, but here we have a politically driven agenda, and this determines where the funds are going. Personally, I did not have any relationship with these funds, I must say that. And that's why I had the freedom not to use the climate models. Well, I used, but as I tested, but not used in studies. And I have showed that if we used those models for the management of the Athens water supply during the drought, then the results would be very, very bad. So I feel myself lucky that I did not get any euro from those funds. And I prefer to have freedom rather than money. Well, the other part of the question is which water-related issues could the research go? Of course, there are many. I could list hundreds, perhaps, hundreds of issues. But what I would prefer, for instance, in hydrology, we speak about hydrology, the International Association of Hydrological Sciences has listed 23 unresolved problems, which could be part of the funding priorities, for instance. But my personal taste is that the researchers make the proposals. They are let be free to make the proposals. And if the proposals are good, they are funded. That's my view.
Is there any comment from Louis and Antonio on that? Before we go ahead, because there are many questions now.
I forgot something funny.
Yes.
During this summer, I had a proposal from a colleague in architectural engineering school to contribute to a study about the archaeological, the protection of archaeological sites. And I said, yes, it's very interesting. I could collaborate and contribute to this research. And she said, yes, but you have to predict what will happen in 2100. I don't remember exactly. And use these scenarios and say, no, I can't do only stochastic predictions. No, the term is that you should use this climate model outputs. And I say, I'm sorry, I do not want to get involved in such nonsense.
Okay, let me move to the next question. This is again for Demetris Koutsoyiannis about water vapor amount. Why IPCC evidence that is the principal forcing for extreme precipitation, considering the PPT of your presentation, Demetris, including the future.
Yeah, I believe the whole story with IPCC is based on a very simplistic representation of the climate. We have the humans that are bad at produce CO2. Then this CO2 increases the temperature. Then there should find a link, a simplistic link with with precipitation and hydrology in general. And this link has been the Clausius-Clapeyron equation, which says, what it says is that when you have increased temperature, then the presence the maximum of the presence of humidity in the atmosphere is increased. But you see, it is not the actual, but the potential. The potential capacity of the atmosphere to contain some amount of water vapor. Okay, this is a very sensitive point. So then the conjecture is that when we have a higher potential for presence of water in the atmosphere, the relative humidity should be constant. And under this condition, also, if the relative humidity is constant and the potential higher, then you should have higher presence of water, and then you should have more intense hydrological signs. But the conjecture should be tested by data. I have done this work, and I believe the whole story is falsified. But beyond that, I believe that the entire story of that I described before, CO2, temperature, water, is too simplistic, because the climate is a very, very complex system, and there are a huge number of factors affecting it. And even the relationship between CO2 and temperature is not clear. And we have published a paper last year with together with Demetris Koutsoyiannis, who is very well-known scientist, particularly in the IPCC, because he has been lead author for water. And we questioned the direction of causality between CO2 and temperature. And our analysis of data shows that the principal direction is from temperature. Increased temperature increases the CO2. Thank you.
Okay, thank you very much. I have to ask Sarah if we can extend, because it's almost 6 o'clock. Can we extend, because we do have many questions?
Yes, if you want, we can extend 10 minutes and then close the webinar.
Okay, thank you, Sarah. Thank you very much. So the next question is for, please keep your answers as concise as possible, and in order to have time to answer all the questions posed. So the next question is for Louis. Dear Professor Garrote, thank you for your insightful presentation. According to your findings, we are already experiencing changes in runoff, and we are expecting strong reductions of, however, according to the presentation of Professor Koutsoyiannis, any changes already observed are due to internal variability, and any projections should not be trusted, parenthesis, even when explicitly considering different sources of uncertainty, parenthesis close. Could you please comment on this?
Okay, that's an easy question. Thank you, because the one on groundwater availability was difficult to answer, but I think this one is easy. At least in Spain, we have observed reductions. I think in Sicily, there's also a clear state of mind that we have experienced reductions in precipitation and in runoff, maybe in other regions in Mediterranean Europe and in other places. That does not necessarily mean that they are due to anthropogenic climate change. It's simply that we have observed such reductions. They could be reductions, and there could just be that when we started measuring, which is probably after the Second World War in 1950s, 1960s, that was a relatively wet period, and that sort of distorted our starting means. And we have seen those means to decrease over time, only because the first 10, 20 years were extremely wet, at least in Spain. However, who cares if that is due to anthropogenic climate change or to other factors? We just have to adapt this. That is long-term changes. It's not changes from year to year. They develop over 20, 30, 40 years. You better adapt to that. You cannot wait until the mean goes back to normal to carry out your life. So we've been adapting, at least in Spain, we've done major work in adaptation regarding water management. We now use, in irrigation, we started using over 10,000 cubic meters per hectare. We are now close to 5,000, almost 50%. In urban consumption, likewise, we had allotments of 400 liters per person per day, and that is down to much less than 300, especially in big cities. So we've come a long way in adaptation, and this is what we should be doing. Projections, I think they are only useful for the purpose that Antonio mentioned at the end of his talk, just to convince people to act. Just like people in Athens started doing things when there was a big drought, and that was a strong motivation at the political level to do things that all technicians knew that they were good and had to be done. But unless there is a big drought, there is not such an emergency to allocate funds for that. And climate change is a good opportunity for getting things done. So the key idea is adaptation, and adaptation comes regardless of whether the change comes from anthropogenic climate change or from other factors. And by the way, social change is much orders of magnitude larger than climatic change. So the way society has changed is much, much, much more than the small amount that a time series of runoff of precipitations have been changing over time. You cannot compare Spain in 2020 with Spain in 1980. And I think this is also the case for Greece, for Italy, for everywhere in the world.
Okay, thank you. That was a question, comment by Aristides Koutsoyiannis. I forgot to mention it. Now there is another question for Antonio by Irfan Shah. Predictions about future is sometimes not as expected, but of course we have to focus on models presented and the recent trends. I wish Professor Antonio Cancelliere to comment about the reused water and its recyclability to control the water scarcity. Antonio? Your microphone
I already answered that question actually on the chat, but very briefly.
Okay, I'm sorry.
Obviously, water reuse is one of the key assets that we have to fight water scarcity. No doubt about that. Still, there are some open problems, which I would say they are not technological so far. I mean, I think technology is already out there and it's growing and growing. But there are some more, say, social-political questions that should be solved first. And this is especially true, for instance, for developing countries. So if we expect that developing countries face water scarcity by investing in water reuse, who's going to pay for the extra cost? Will the end users be willing to pay for that extra cost? So I think, again, I think that the problem is not really technological. It is more a social political one, of course. And
Antonio, there is another question by Ricardo Mandilla. I'll read it, and probably I don't know if you have answered that. Dr. Cancelliere, you made a number of conclusions regarding the interpretation of SPI in the context of droughts. I want to hear from you if this transfers to other indices that use some kind of water accounting, such as Palmer Index, the Palmer Index?
Yes, I will be very quick in my answer. The answer is yes. Of course, this extends to all the standardized indices. Palmer Index use a different kind of accounting mechanisms, but
Water balance index.
yeah, it's based on the
It's a water balance index.
The water balance based, but it has also a very strong, exhibits also a very strong autocorrelation. So you know, whenever I have this type of series with very strong autocorrelation, I have to be very careful when I make conclusions about trends or other kind of changes.
Okay, thank you very much, Antonio. There is a question by Dr. Nectarios Kourialas. I have a general question. As Professor Koutsoyiannis mentioned, surely the advantages in forecasting and adaptation methods of flash droughts / floods have significantly minimized human losses. But the question is, what about the losses in food production in the agricultural sector? Do we have data about the effects of these extreme hydrological events in the agricultural sector in comparison to other risks, for instance, in the Mediterranean area? Do you want to answer this question? The question has to do about the agricultural sector, the food production, and the impacts of extreme events, and probably the climate change and the changes in these extreme events, droughts and floods. Yes, Dimitri. Yes.
Yeah, I think well, I do not have data, and I haven't studied data, so my reply will be perhaps misleading. But of course, there is a risk for agriculture because of floods, etc. But if we see the entire picture, during the last 50 years, there was a tremendous progress in agricultural production, and now the population of which has become 7-point-something billion can live because of that spectacular improvement in agriculture. Am I wrong? Yes, the entire picture is very, very positive in terms of agriculture. And to this also, I would add that there are some couple of articles from NASA, I think, that have shown. I can find if the colleague who asks has interest, I can send the articles. These are not mine. Which prove that our planet has been greening in the last 30 years, perhaps because of the increased CO2, and also because of the human management, improvement of management techniques in areas that are cultivated. For instance, India and China have a very large contribution in the greening of the planet.
Yes. Any comment from Louis and Antonio on that? If there is not.
No, it's true. It's true that you know, for instance, in the irrigation sector, of course, there have been many advancements. If you think about, if we take a look at water demand for irrigation in Sicily, and in particular in the Simeto watershed, basically the demand has not changed over the years, although the irrigated areas have increased a lot. And so that tells us that you know, the specific demand has basically decreased compared to what it was 20-30 years ago. So this kind of, and the other thing also is that following the droughts back in the 90s, many small reservoirs have been built at a farm scale, which of course reduces vulnerability to droughts for the farmers, and so therefore I think that overall the effect of these extreme events is really to have farmers that are more prepared for them. So we may argue that if you make a balance, maybe overall the effect of these extreme events has been positive.
Okay. I think we're coming to the conclusion of this webinar. Before we go to that, I want to ask the three speakers if they have a comment, a general comment, before closing.
I have one comment.
Yes, please.
Yeah. I'm very happy for this discussion, for the questions of the colleagues in the audience, and as well for the presentations of the two other colleagues. I'm very glad that we have disagreements and also agreements. I particularly liked, appreciated both presentations, and I particularly liked that Antonio Cancelliere referred to Slutsky theorem and his papers, and as well as to Witt-Clemens papers. Well, this analysis of time series, which is the basis of our analysis in hydrology, has started from economics, from econometricians. I think Persons was the first to propose these methods, and he made several errors. For instance, he sorry, I'm a little bit tired now and I cannot find the word. He separated the time series into trends, periodicity, cycles, and and random components. And Slutsky proved with his theorem that one of the three, that is the cycles, is fake, is artificial. So I'm very glad that Antonio presented this. And I also believe that in the future, the trends that we use today will be proved that they are also artificial. And perhaps if you see the nilometer data that I showed you, that had huge fluctuations, which if we have only a small part, we could view as trends. In fact, they are fluctuations. So that's my final comment, and I would like to thank you. And I'm particularly glad, again, I repeat it, because all the three of us view adaptation as the key to what will happen in the future, as our driver for the future.
Okay, thank you, Demetris. Yes, Antonio.
Yes, I appreciated the fact that despite some apparent differences, maybe that can be explained in terms of Slutsky theorem, who knows? But I think we have basically the same view in the sense that even if you talk about the fact that these apparent trends are not really trends, but not just fluctuations, if you put everything in big perspective, and but still this doesn't mean that we have to do nothing about it. You know, I appreciated Louis' presentation about adaptation, which I think is key. Even, you know, regardless of the fact that you believe that these fluctuations are just natural or human induced. I tend to prefer the first explanation personally, but of course, you know, as water engineers, I think that we have to deal with the fact that there are this fluctuation. So I really appreciated this part of the of the discussion. And the other thing, if I may, I fully agree with Demetris on his attitude against any type of say climate change studies in the orthodox way as it is meant. And because I think that the danger, if you know, even if you don't really believe in those things, the danger is that, as you said, you know, is that climatologists, or who knows, physicists or experts of physics of the atmosphere will be the ones that will design the next reservoir for Athens, or maybe the next reservoir for
absolutely
for Decimeto. So the danger,
that will happen for sure.
Yeah, I know, but the danger is, you know, if we go on the Aventino, we say, you know, the Aventino is this hill in Rome where in ancient Rome they would go up there to kind of isolate themselves from the rest. If we go to the Aventino, the risk is that people will do the job for us, and presumably in a much worse way. So I think we have to find a balance between, you know, people that are truly believers in climate change models and your attitude, which again, it's not that I disagree with your point of view. I just think that when we have to be water engineers, we have to find some compromise for the greater good.
Probably the truth is somewhere in between. Louis, do you have a comment, a last comment?
Well, very briefly, because I think we are losing participants asymptotically, so we have to conclude. I think that adaptation, as we all agree, is key, but I would like to go one step further, because I think that in water management, adaptation, what we understand by adaptation, which is preparing ourselves for less water availability, for more floods, for more long and frequent droughts, and all that. All these catastrophes linked to climate change are unfavorable for water management. So I would say that adaptation is good by itself. Even if there is no climate change, it is a good thing to do. Saving water, using water more efficiently, using more technology, developing new technology to deal with water, that is good by itself, even if there is no climate change, even if there was no change in the natural time series that we base on.
Make things better.
It is good by itself. So it's not good only to cope with climate change or with anthropogenic or with global change or whatever changes we have to face. It's good even if there is no change, because for sure there will be social change. We will grow, we will use more resources, we will enjoy life more, and that implies that we have to use our resources more efficiently. Also because
there will be change.
Yeah.
But there will be change. We can be sure that there will be change.
There will be change, and
everything changes.
Adaptation is good by itself. Panta-Ray. So even in other areas of climate change, like, I don't know, sea level rise, you have to think very carefully when you have to make an investment in building infrastructure, which is specifically designed to cope with sea level rise. In case of water management, what we do is good by itself. I'm pretty sure of that.
Okay, thank you very much. Just a final closure. for me, 1 minute. So I want to thank all the participants, the three invited speakers for the intriguing and interesting presentations, the fruitful discussion in this webinar. Of course, I have to thank also Sara Ottolini, our conference assistant, who helped with the technical issues. And last but not least, Rachel Liu, the assistant editor, who helped me to set up and organize this webinar. This webinar is the third of a series of water MDPI webinars, and many other webinars will follow. Thank you very much, all of you, cordially, and hopefully we'll see each other in person in the near future. Okay, thank you very much. Bye-bye.
Thank you
Thank you very much. Just one final remark. The recording of the webinar will be made available as soon as possible on the webinar's webpage, and all the participants will receive a notification about that. Thank you very much, and bye-bye.
Okay, thank you. Bye-bye.
Bye-bye.